Hello, we're going to be talking about multidimensional Cartesian coordinate systems and equations. It helps to start with one dimension and then move up to more than one dimension. In one dimension, of course, everybody is familiar with the number line. We have 0 somewhere. We define a unit. Typically, we put positive numbers on the right and negative numbers on the left. And the set of all the points on this line can be also written as R for real numbers. And we denote each point on the line with a number. So this is 1. And then over there, we will have 2, 1.5, somewhere in between 1 and 2, and so forth. In 2 dimensions, 2D, we have 2 axes. This line keeps going on to the left forever, and this line keeps going down forever. We label this axis typically as x-axis and y-axis. We define a unit where the axes intersect, that is the mutual 0 of those axes, and where they intercept, we have the origin. There's the unit 1 for the x-axis, and then a unit for the y-axis. All the points on this system are represented with r squared, as opposed to just r. And the way we locate a point in this system is with 2 coordinates. So for instance, if we want to locate this point, we label it as 2, 1. It is important to distinguish 2, 1 with 1, 2. The order in which we write the numbers as we represent points on this coordinate system is very, very relevant. By the way, some people think that the r is inside of the r squared, and that is not quite correct. There is a copy of r here, but actually there's many, many copies, because you could have r going this way, or you can have r going up and down, or you could have r going diagonally. So when we say that r is inside of r squared, we gotta be careful. We have to match. A copy of it could be inside if we match it correctly. That's all I'm going to say about that. But we just got to be careful about stating whether r is inside of r squared. And now we go into 3 dimensions, 3D. We got the z-axis, the y-axis, the x-axis. And typically, this is the way we write our 3-dimensional coordinate system. This axis over here is called the x-axis. And then we have the y-axis and the z-axis. I cross my z's to distinguish them from 2's. The point where all the axes intersect is called the origin. We define a unit. So this is 1 on the x-axis, a 1 on the y-axis, and a 1 on the z-axis. And to locate a point in this coordinate system, we need 3 coordinates. So for instance, the point 1, 2, and then 3 would be, well, 3 is too high, so let's make it a 2. So, well, that's a little short there, a 2. So this point would be 2, comma, 1, comma, 2. Again, the order in which we write the coordinates is very relevant. The first number tells us how far we go on the x direction. The second number tells us how far we go on the y direction. And the z tells us which way we're going, up or down. It is rather difficult to draw things in 3 dimensions on a 2-dimensional piece of paper. Practice, that's the thing I can tell you about that, to practice. Let's talk now about distances and magnitudes. Distances and magnitudes are pretty much going to be the same. If we have the 1-dimensional line with 0 in here, and if I say, if we write the equation, the magnitude of the points has to be equal to 3, the points on this line that satisfy that equation are the points that are 3 units away from the origin. So if we go 1, 2, 3, we got one solution to this equation. And then if we go 3 units on the left, we're going to be having another solution. So this equation on the 1-dimensional space, so 1 dimension, or R, this equation has 2 points in the solution. If you have the same equation in 2 dimensions, 2D, all right, we will have, so again, same equation in 2D, we'll have a different set of solutions. So we have 1, 2, 3, there is one solution. Again, this equation states the distance of a point P to the origin should be equal to 3, and there is one. And then there is another one up here. But wait a minute, there is one on the left, 1, 2, 3. And then there is another one down, 1, 2, 3. But wait, there is more. There is one diagonally 3 units away, so maybe there. There's one diagonally in the opposite direction, about there. There's another one on the diagonal opposite here. And then another one down here. And then there is another one in between. Once we get into 2 dimensions, this equation is satisfied by hundreds and hundreds, an infinite number of points. In fact, when we draw all the points that are 3 units away from the origin, we end up with a circle. So this equation represents a circle in 2D. This equation represents 2 points in 1D. From that perspective, we could think of those 2 points in 1D as a 1-dimensional circle. This is a 2-dimensional circle. And then the same equation, I'm going to write it again. The distance of a point P to the origin should be 3. The only reason I'm writing it again is because I'm shifting this down. So if we have 3 dimensions, and you have that equation, the points that will satisfy that they are far away from the origin by 3 units are going to be, well, there's going to be one on the x-axis around there, 1, 2, 3, 1, 2, 3. But then there are points on the left, our left, and back here, 3 units, and down here, and then diagonally in every possible direction. So by the time we finish this, we're going to end up with, well, round here, and then round there, and round here, and round all the way around. So we end up with a sphere. So one could think of this sphere, since it came from this equation, as a three-dimensional circle. And then this one is the two-dimensional circle as the way we know them. And then we have a one-dimensional circle, or somebody can say, wait a minute, this is a sphere. Perhaps we should call this also a sphere, a two-dimensional sphere, and that would be a one-dimensional sphere. I don't think it matters what we call it, as we understand that this equation is the one that is generating all the points that take those shapes. The way we measure distances practically, so let's talk about distances. Okay. If you have two points on the number line, it doesn't matter where 0 is. If you have 2 points on the number line, lowercase p and lowercase q, then their distance is the absolute value of the difference between p and q. If we know in advance p is to the right of q, then we know their positive distance will be p minus q. But when we are solving equations and when we are working with variables in general, we may not know whether one number is ahead or behind the other. So the distance, let's call it d for now, between p and q will be the absolute value of p minus q. Absolute value works very well as far as the concept, but it doesn't work very well algebraically. Because if we want to do derivatives or integrals with absolute values, then we have to break the problem up into parts. Sometimes it is better to use just an algebraic operation. And the one that works, or some kind of function rather, the one that works reasonably well is the square root of the quantity p minus q squared. So the distance between p and q can be written as the square root of p minus q quantity squared. By squared, we are making sure that this number will be positive before we take the square root, bring it back just the pure number without being positive or negative. In two dimensions, we have 2 coordinates for each one of the points. So we could have AB and XY. And Pythagoras says the distance between those 2 points is, well, if you draw vertical and horizontal lines, we will realize that this is actually the hypotenuse of a right triangle, and one leg will be b minus y, while the other leg's length will be x minus a in this case, in this kind of situation. But again, we don't know which one is going to be ahead, which one is going to be behind. So by squaring, we don't have to worry about that. Besides, Pythagoras squares the legs of the triangle anyway in its formula. So the distance between those 2 points is going to be the square root of a minus x quantity squared plus b minus y quantity squared. And it doesn't matter in this case whether we do a minus x or x minus a, because when we square this quantity, we're going to end up with a positive answer anyway. Either way, we're going to end up with a positive answer. So that is how we compute the distance. Let me go back here. This length is what we label as d, and this length is what we label as d. Okay. In 3 dimensions, we have the same kind of situation, By the way, in my last page, or one of my last pages, I did not mention that this can be written as r cubed. Yeah. By the way, r squared is not necessarily inside of r cubed unless you make a proper embedding of one into the other. But we cannot just assume one is inside of the other because there are many ways to place r squared into r cubed. So they're not really one inside of the other. We can embed one into the other. That is the proper word to use. If we have 2 points up here, somewhere, say here, so that is A, B, C, and another point maybe down here somewhere, X, Y, Z, then the distance between the 2 points is going to be a generalization of those 2 formulas. As you can tell, whoops, these 2 formulas. If we have 1 dimension, we just subtract, square, and take the square root of the coordinates. If we have 2 dimensions, we do the same thing, respectively, add them together, and then take the square root, square the 2 differences. So it would make sense down here to do exactly the same thing. We take the square root of a minus x, quantity squared, plus b minus y, quantity squared, plus c minus z, quantity squared. It is neat to see how the formula continues being the same, whatever the dimension is. You can interpret this geometrically on 3D if you draw the correct triangles. You will see that you get this formula. But the reason why this formula is valuable to see in terms of 1 dimension, 2 dimensions, and 3 dimensions is that in 4 dimensions, so 4D, we can do exactly the same thing. If we have a point, A, B, C, D, and another point, X, Y, Z, W, we can find the distance between those 2 points. And as you can predict, probably, is that the distance will be a minus x, quantity squared, plus b minus y, quantity squared, plus c minus z, quantity squared, plus d minus w, quantity squared. Yeah. And then you can extend this to any dimensions. I don't draw 4 dimensions pictures. I decided a while ago not to draw 4-dimensional pictures. I don't know how to. So some people think about 4 dimensions very, very deeply. I don't, and I'm okay with that. It is a little bit like flying with instruments. My instruments are my formulas and equations and so forth. Okay, let's talk about equations next. So it's equations. It is a little tricky to talk about equations initially. Let's talk about the equation x equals 2. In 1 dimension, that equation has 1 solution. So this is the origin, then 2, and that is a 1, then 2 will be this point. So this equation represents this point. There's no drama involved in this setup. There's a little bit of drama when there are 2 dimensions. So I'm going to rewrite x equals 2, same equation, but now we are in 2 dimensions. When we say that x equals 2, that is really a shorthand for a big set. I'm going to write this set down here. So x equals 2, by that we mean the set of all the pairs x comma y, all of them in r squared, so in this plane, such that x equals 2. That's it. And there is no requirement for y. So in this notation, we mean all. It is, we typically don't write it, but we mean all possible x, y's in the plane so that x is 2. And there's no restriction on y. So y could be 5 or 7 or 13 or 0 or negative 5 or pi or e, etc. So if this is a unit and this is the number 2, this point would be 2, 0, 2, 0. That point satisfies this requirement. Now, this is a little confusing because when we see x equals 2, we perhaps may be thinking 1D. But if we are in 2D, we mean this set, which is way different than just this one point. So we have to be careful when we look at an equation and realize this is really a multitude of points. You could have 2, 1, 2, 2, 2, 3, 2, negative 1, and so forth. Every one of the points in between. So 2.5, 2.1.5, 2.5, and so forth. And then 2 1/4, well, 2, comma, a quarter, etc. So we got all the points on this vertical line. So x equals 2 represents this vertical line in 2D. So this is a 2D. So the equation x equals 2 in 2D is represented by those points. All of those points satisfy that equation. X equals 2 in 1D is satisfied exclusively by a single point. Okay. So in 3 dimensions, 3D, if we have x equals 2, okay, so before I start drawing, let's understand what we mean by this. We mean the set of all. We typically don't write all. It is understood. The all is understood. Let's put it in parentheses. All possible x, y, z in r cubed such that x equals 2. And then that is the end. Now, it is important again to realize that we are talking about all possible x, y, z. That means that we have 3 coordinates involved in this picture. And the only requirement is that x is 2. Y and z may be anything. And since we are stating that we want all the possible such points in a 3-dimensional space, well, there's many of them because y could be 100 or 1,000 or -2 or any number. Same with a z. So when we start drawing the picture, we have 1, 2. So this point is, oops, sorry, I did this wrong. This is the y-axis. I better not confuse my axis. The x-axis is typically this one. So please neglect that point. So there's this first point, 2, 0, 0. And then we can have 2, 1, 0, and 2, 2, 0, and 2, 3, 0. So all the points on this line, as well as the points back there. But we could go 2, 0, 1 up here, 2, 0, 2, 2, 0, 3, 2, 0, negative 1. So all the points on this vertical line through this point, all the points through this horizontal line, through that point, and every point on the plane where those two lines reside. So we got a plane here that is parallel to this plane back here. By the way, this plane, I neglected to mention that this plane is called, on the back, the YZ plane, YZ plane. The floor is labeled as the XY plane. And the sidewall on the left is labeled as the XZ plane. XZ plane. So we have three planes. And by the way, those planes do extend to the left, down, and back there. So going back to the equation, x equals 2 represents a whole plane. Now, realize that x equals 2 represents a line in 2D, a point in 1D, a plane on 3D. In 4D, we would have something else. I have to think about that for a moment. I don't want to say it right away because it could be misleading. All right. Okay. After thinking about this for a moment, I realized that x equals 2 in a 4-dimensional space would be a solid or a space. A 3-dimensional solid or 3-dimensional space embedded into a 4-dimensional space. And again, I don't draw 4 dimensions. If you want to draw 4 dimensions, go for it, but I'll not do it. Let's talk about orientation for a moment. Orientation. As we talk about equations, so this is within equations. Let me start a new sheet. So orientation. If we have the equation y equals x squared, you should be quite familiar with this equation. The graph of this is a regular parabola. The parabola is not quite too smooth, but that's all right. This is the x-axis, and this is the y-axis. And most people are familiar with that. So the question is, what about this equation in 3D? This is y equals x squared in 2D. What about y equals x squared in 3D? It's a question mark. So we draw the picture, the x, y, z. Let's extend the x. So we have some of the negative x's. So this is again the x, y, z axis. Origin is where they intersect. And the parabola will open to our right. So that is the same parabola. Well, I shouldn't say the same one because they're different. But on the xy plane, we have the same kind of picture. Pretend this is the xy plane, and then the picture would be the same. And we see the picture sideways because the xy plane is placed horizontally versus vertical in front of us. This is horizontal. All right, but there's more to it. Okay, so when we have this equation in 3D, what do we mean? We mean all possible x, y, z in real numbers such that y is x squared. So we have a condition. If x is 1, then y has to be 1. If x is 2, then y has to be 4. But if x is -2, y has to be 4 as well, just as with this parabola. But we want the set of all possible x, y, z's. So if z is 7, well, that still satisfies this requirement. So I'm not going to draw 7, but if it, so if we have 1, 1, well, let's do 1, 2, rather, sorry, 2, 4, it's going to be over here somewhere. And then we can go up to a z of 7, maybe. Well, I guess I can do 7, maybe, if we pretend that is 7, or -3, or -2. So the vertical line going through this point, actually all the points on this vertical line through this point satisfy this equation or this condition. But then the same thing is going to be true about all the vertical lines through points that are on this parabola. So we end up with a surface that wraps around here, goes around, and then it continues this way. So we have a vertical surface, it goes up and down, and it curves just like a parabola. So the top view, if we were able to see this from the top, would look like a parabola. But then when you see it in 3 dimensions, you can see that there is an area to it. There's a surface to this. This is called a cylinder. So when you let one variable loose, such as in this case z, then you have what people call a cylinder. Yeah. So this is a cylinder. It is very, very important to notice the orientation of this cylinder. We're going to play with this a little bit. You should become familiar with the orientation of these cylinders. So a new example, let's say z is equal to x squared. In this case, the y is free to be whatever it wants to be. So we have a parabola. You can extend the x-axis. This is an arrow. And these are the x-axis, y-axis, z-axis. And the parabola, if y is equal to 0, would look like this. But then any horizontal line that goes through the points on this parabola will also satisfy the equation. So we have a cylinder, but this cylinder is, and let me draw a different picture, a little nicer picture. As you can tell, you really want to practice this. So one way to think of this cylinder is to draw it this way. These 2 points are supposed to connect, and then we have that, and this continues going this way, and this goes up. If we place the origin there, the x-axis this way, the y-axis that way, the z-axis this way, there is our cylinder. Z equals x squared. Not to be confused with y equals x squared. So this cylinder goes up, down, straight up, down. This cylinder goes straight horizontally this way. So you should think, what is the other? There are 6 combinations that we could have. Let's write all 6 combinations. You can have y equals x squared, z equals x squared, but then we could also have x equals y squared, x equals z squared, that's 4, yz, y equals z squared, and z equals y squared. Each one of those will represent a different cylinder in 3 dimensions. Do practice this. I strongly encourage you to practice to draw all of those 6, because we have to develop an intuition about how to draw things in 3 dimensions. Our next equation is going to be the equation of the circle. So we have distances, so let's talk about circles. And we are still under the same umbrella of equations. Circles and spheres. Although we can assume, or we can work on the assumption that a 3-dimensional circle is a sphere, a 2-dimensional sphere is a circle. We can go back and forth because the equation is very similar to one another. So we should know that the equation of a circle on the plane and on the xy plane is x squared plus y squared equals r squared, where r is the fixed radius of the circle. And we can shift this circle. This circle right now is the origin, center at the origin. We can shift it so that if you want the circle to have center at AB, it doesn't matter where AB is, then the way to draw the equation for this circle would be x minus a, quantity squared, plus y minus b, quantity squared, equals radius squared. And the reason for that is because we have the equation of the distance between 2 points. So the distance between the generic point x, y on the circle, so we have a generic point here with coordinates x, y, to its center should remain constant, r. And so we have a square root of that equals r. And if we square both sides of the equation, then we end up with this. So the shift to the point AB, regardless of whether A or B are positive or negative, or a combination, the equation for the circle with the radius r and center in AB in 2 dimensions will be this. The equation of the sphere with center A, B, C in radius, so we got a sphere, a complete sphere. It's a ball. The equation of this circle, sorry, the ink ran off that way, will be x minus a squared plus y minus b squared plus z minus c quantity squared equals this, the radius, whatever the radius is, quantity squared. And there is the equation of a circle in 3 dimensions, which we call typically a sphere. Yeah. Be careful, because this equation in 3D represents a cylinder. If you want a sphere, you have to do this. Yeah. Let's elaborate on that very quickly. So if we have x, y, z, the set of all the possible x, y, z's, such that x squared plus y squared equals 9. Okay, this is a surface on 3 dimensions. The way we can tell is because we have 3 variables, x, y, and z. But z can be any number. Z is not restricted to any requirement. So the equation of this cylinder, and this will look more like a cylinder, like the cylinders we know, is going to be, well, from the top, This is going to look like a circle, but then it has walls going up and down. So this is your typical cylinder. It's a typical tube. It goes up without any bound, and it goes down without any bound. And again, as we did with the other example of the parabola, it is a good idea to go over all three possibilities of cylinders. So this is going to be, the equation for this cylinder is x squared plus y squared equals 9. By the way, the radius is 3, 1, 2, 3 units. But you should try to draw x squared plus z squared equals 9. And y squared plus z squared equals 9. A question that comes to mind is, how come with the parabolas we had 6 possibilities, but with circular cylinders we only have 3? We don't have 6 as in the parabola. Think about that, please. We're going to finish up with one example that I want to develop for an equation. Let's say we want to find, so this is a bigger example, let's just call it example. So we want to find equation of all points, comma, in 3D, so x, y, z, that are equidistant to the plane z equals -1 and the point 0, 0, 1. So we want to find the equation of all the points x, y, z that are at the same distance from a plane, this plane that is under the x, y plane, and a point. Let's draw a picture of what's going on first, and then we're going to start solving this algebraically. So we got the three-dimensional space, x, y, z. The plane z equals -1 is a plane that is down here, 1 unit below the x, y plane. So this is below. You're going to go down to find this plane. And it is a horizontal plane. The point 0, 0, 1 is up here. And we want to find all the points that are equidistant from the plane as well as from the point. So one point is clear, this one, 0, 0, 0. That's part of the solution of this problem we're solving. One point here on the right will be, if it is, it gets complicated because, let's see, we want 1 unit. We cannot have more solutions on the y-axis. If we want a solution that is not the origin, we have to be off the y-axis, off the plane, xy plane. So maybe here we will find a point, that is same distance from this as from the plane. So we want all the points whose distance from this point, fixed point, this point is 0, 0, 1, is the same distance as this. You should be a little familiar with this kind of situation. We have done this in 2D and the solution is a parabola. In 3D, the solution is a paraboloid, which is going to look sort of like a parabola. I'm going to start this problem, and I'm going to let you finish it, if that's okay. All right, so we want all points whose distance to the point 0, 1 is the same as the distance to z equals -1. All points. So let's talk about those distances. The distance, okay, so distance from x, y, z to 0, 0, 1 is the square root of x minus 0, so that's just x. Well, let's write it down, x minus 0 plus y minus 0 squared plus z minus 1 squared. Okay, while, so we want all points whose distance from xyz to is same as distance from x, y, z to z equals -1. Now let's think about this for a moment. If you have a point with coordinates x, y, z, or a, b, c, whichever, and you want to know how far it is off down here, the plane that is 1 unit below the xy plane, below the floor, the coordinate that tells us the distance from the floor to this point is going to be z. But this distance, let me draw it a little better. This is z, is in addition to the distance from the floor to the plane. So the total distance is z plus 1. The total distance from the point to the plane will be z plus 1. The distance from x, y, z to z equals -1 would be, there's another way to think of this, which is more of a formula. If you want any vertical distances, you do subtract the top minus the bottom. So whatever the z value is of the point minus the bottom, which is -1, and that gives you z plus 1. Now, z plus 1 could be positive or negative, depending on the value of z. And we want to end up with positive solutions only. So we are going to artificially make this, we're going to make this positive by taking the square root of z plus 1, quantity squared. And that will assure us that we end up with a positive solution. Technically speaking, we should have started with an absolute value here, absolute value there, and now that makes the equation a correct equation. Otherwise, if z was negative, then this equation wouldn't necessarily be correct. All right, so those two distances have to be the same, which means that x squared plus y squared plus z minus 1 squared has to be the same thing as z plus 1 quantity squared. And let's simplify this. That means that I think I have enough room to simplify it here. Let's see. X squared plus y squared plus z squared. We FOIL this out, minus 2z plus 1 equals z squared plus 2z plus 1. And of course, we subtract 1 from both sides of the equation. We subtract z squared from both sides of the equation. And we add 2z on both sides of the equation. So we end up with the equation, and I'm going to put the 4, I'm going to switch the sides. So 4z is going to be the same as x squared plus y squared. So there is our equation of the surface where every point is equidistant to the plane z equals -1 and the point 0, 0, 1. This is represented with a paraboloid graphically. Let me show you paper. So for z equals x squared plus y squared is going to be a paraboloid like that. It is a surface. It goes around this way. And what is important about this paraboloid is that, again, the distance to, let's say this is 0, 0, 1, every point on here is the same distance to 0, 0, 1 as to the plane z equals -1. So the distance from this point down to 1 unit below the xy plane will be the same distance as this. I think this is a good problem and a good place to stop. Oh, well, but I like to move things around. It gives us a better idea of how to graph this. What if you had 4y equals x squared plus z squared? Or 4x equals y squared plus z squared. In fact, we could have, no, I think that's it, three possibilities. Yeah, if we want all the numbers to be positive, all the coefficients to be positive rather, we only have 3 possibilities. So it is a good idea to draw those two. They're going to be similar to this picture, but not the same. And with that, we finish this first part of multivariable calculus. Thank you.